Hello there and welcome back to the Science Sleepy Minds. You're lying somewhere soft right now, aren't you? Maybe your bed, perhaps a couch that's slowly absorbing your outline like quicksand made of cushions. The ceiling above you seems close enough to touch, maybe 8 feet away, 10 at most. You could throw a sock up there if you wanted. You won't, because you're tired, but you could. That ceiling feels like a reasonable distance. Understandable, human-scaled. Now imagine that ceiling is 4 light years away, not 4 feet, not 4 miles, 4 light years. That's roughly 23 trillion miles, give or take a few billion, which at this scale hardly matters anyway. Your sock would need about 50,000 years to get there if you threw it at the speed of a professional baseball pitcher. And that, my friend, is just the distance to the nearest star that isn't our sun. The universe looked at human comprehension, laughed softly, and then kept stretching. Tonight, we're going to break your brain. Gently, of course, with care and affection. But we're going to take your comfortable understanding of distance, the kind measured in steps to the refrigerator or hours to your grandmother's house, and we're going to stretch it across the cosmic void until it snaps like an overtaxed rubber band. You probably won't survive this journey with your sense of scale intact. Nobody does. Astronomers have been walking around with shattered spatial intuition for centuries, and they seem mostly fine. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in, drop a comment telling me where you're listening from and what time it is there. I love knowing that someone in Tokyo and someone in Toronto might both be staring at their ceiling right now, contemplating the same incomprehensible distances, separated by mere thousands of miles, which after tonight will feel like nothing at all. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. The light year is humanity's most ambitious tape measure. It's what happens when regular numbers throw up their hands and surrender. When astronomers in the 19th century started mapping the cosmos with any real precision, they quickly discovered a problem that would have been funny if it weren't so cosmically humiliating. Their units were too small. Laughably, embarrassingly small. Think about it. A mile was invented to measure roads between towns. A kilometer was designed to help you understand how far it is to the next village. These are human distances, built for human legs walking across human landscapes. They work beautifully when you're calculating your commute or planning a road trip. They become absolutely useless when you're trying to describe the gap between stars. Imagine trying to measure the Pacific Ocean using only the length of your thumbnail. Technically possible, mathematically sound. But you'd be writing numbers so long that you'd run out of paper, patience, and quite possibly the will to live. That's what happened to astronomers trying to describe cosmic distances in earthly terms. The star Proxima Centauri, our nearest neighbour beyond the Sun, sits roughly 40,208 billion kilometres away. 40 trillion. The number is correct, but it's also meaningless. Your brain sees it, acknowledges that it's large, and then quietly files it away with other incomprehensible figures like the national debt or the number of unread emails in your inbox. So scientists did what scientists do when reality gets inconvenient. They invented a new unit. They looked at the fastest thing in the universe, light itself, and asked a simple question. How far can light travel in 1 Earth year? The answer became the light year, a distance of approximately 9.46 trillion kilometres. Still an absurd number, but at least now you only need single digits to describe nearby stars. Proxima Centauri, about 4.24 light years. Suddenly manageable. Suddenly something your brain can hold without immediately dropping. The light year isn't really about distance, though. That's the secret they don't tell you in school, probably because it would cause existential crises in middle schoolers, and frankly they have enough problems with algebra. The light year is about time. It's about how long information takes to travel across the void. When you look at a star 4 light years away, you're not seeing it as it is. You're seeing it as it was 4 years ago. The light hitting your eyes right now left that star when you were 4 years younger, when you hadn't yet made several of your recent questionable decisions, when the world was different in ways you've probably forgotten. You're never seeing the universe as it is. You're always seeing the past. The sky's a museum, and the exhibits have been travelling to reach you for years, centuries, millions of years. Some of the stars you see tonight might not even exist anymore. They could have exploded, collapsed, vanished entirely. But the news hasn't reached us yet because the news travels at the speed of light, and light, despite being literally the fastest thing possible, is still heartbreakingly slow when faced with the scale of space. Scholars still argue whether the light year should even be considered a proper unit of measurement or just a convenient approximation. Some astronomers prefer the parsec, which sounds like something from a science fiction movie and involves complicated trigonometry that we absolutely do not need to discuss while you're trying to sleep. The parsec is about 3.26 light years, making it slightly more unwieldy for casual conversation, but apparently more elegant for certain calculations. There's a rivalry here, gentle and academic, between scientists who prefer their cosmic measurements served in light years and those who insist on parsecs. It's exactly the kind of low-stakes dispute that astronomers get passionate about at conferences, probably while drinking coffee and wearing sweaters with elbow patches. But here's the quirky thing about light years that most people never consider. The length of a light year isn't actually constant, not precisely. Because a light year is defined as the distance light travels in 1 Julian year, 365.25 days, the measurement depends on our particular calendar system. If we used a different calendar, if our year were longer or shorter, the light year would change accordingly. It's a cosmic yardstick calibrated to one specific planet's wobble around one specific star. In that sense, even our most ambitious unit of measurement is still hopelessly provincial, still tied to Earth, still carrying the fingerprints of a species that hasn't yet figured out how to leave its own solar system. You're starting this journey from a small planet, in a modest solar system, in an unremarkable corner of an average galaxy. And you're about to discover just how much emptiness surrounds you on every side, stretching away in distances that numbers can name but minds cannot truly grasp. Light is doing something right now, as you lie there. Photons are streaming through your window, bouncing off your walls, carrying information about everything they've touched. Some of them have been travelling for 8 minutes from the sun. Some have been travelling for billions of years from galaxies so distant they didn't have names until a telescope stumbled across them. Light is the universe's postal service, and it never stops delivering. But what actually is light? This question has haunted humanity for millennia, and the answer is somehow both simple and completely unsatisfying. Light is electromagnetic radiation that your eyes happen to be able to detect. That's it. That's the entire explanation. Light isn't special because of some cosmic privilege. It's special because your biology evolved to notice it. There's radiation all around you right now. Radio waves, microwaves, infrared, ultraviolet, X-rays, and you're blissfully unaware of all of it because your eyes are tuned to one tiny sliver of the electromagnetic spectrum. You're essentially walking around with a radio that only picks up one station. The ancient Greeks had theories about light, most of them charmingly wrong. Plato believed that your eyes emitted beams that touched objects and brought information back, like tiny invisible tentacles feeling up the world. Aristotle disagreed, arguing that light was a disturbance in the medium between your eye and the object, which was closer to correct but still missed the mark by about 2,000 years of physics. The debate raged on softly in scrolls and lectures, while light continued doing its thing regardless of human opinions. It wasn't until the 17th century that things started getting interesting. Isaac Newton, when he wasn't busy inventing calculus or being professionally unpleasant to his rivals, passed sunlight through a prism and discovered that white light is actually a combination of all visible colours: red, orange, yellow, green, blue, violet, all hiding inside that seemingly simple sunshine, separating out like secrets revealed under pressure. Newton believed light was made of particles, tiny corpuscles shooting through space in straight lines. He was partially right, which is often the best any scientist can hope for. Meanwhile, a Dutch scientist named Christian Huygens had a competing theory. Light was a wave, rippling through space like sound ripples through air. He was also partially right. The universe, it turns out, enjoys being difficult. Light behaves like a wave when you set up certain experiments, and like a particle when you set up others. It's both and neither, depending on how you look at it. This wave-particle duality still makes physicists slightly uncomfortable at dinner parties, though they've learned to live with it the way you learn to live with a weird noise your car makes that the mechanic can never find. The speed of light remained a mystery for an embarrassingly long time. Galileo tried to measure it in 1638 by having two people stand on distant hills with lanterns, uncovering them in sequence and timing the delay. The experiment failed because light is so fast that human reaction time made any measurement impossible. Galileo concluded correctly that light was either instantaneous or very, very fast. Not a satisfying answer, but an honest one. The first successful measurement came in 1676, and it happened almost by accident. A Danish astronomer named Ole Rømer was studying Jupiter's moons, trying to predict when they would pass behind the giant planet. He noticed something strange. His predictions were off, sometimes by several minutes. The moons seemed to move faster when Earth was closer to Jupiter, and slower when Earth was farther away. Rømer realized the delay was caused by light taking longer to travel greater distances. From this observation, he calculated that light traveled at about 220,000 kilometers per second. He was about 26% low, but considering he figured this out using Jupiter's moons and 17th century equipment, it was remarkably close. Modern measurements have pinned the speed of light at precisely 299,792.458 kilometers per second in a vacuum. Not approximately, precisely. In fact, the meter is now defined based on the speed of light, making it a fundamental constant rather than a measured value. Light travels 299,792.458 kilometers in 1 second, and a meter is defined as the distance light travels in 1 divided by 299,792.458 of a second. The speed of light doesn't match the meter anymore. The meter matches the speed of light. Scientists essentially said, light wins, and will adjust everything else accordingly. This speed is almost impossible to internalize. In 1 second, light could circle Earth's equator roughly 7.5 times. It could travel from London to New York and back about 25 times before you finish saying the word hello. If you could somehow run at the speed of light, you would experience time so strangely that the universe would age around you while you barely noticed. But you can't run that fast. Nothing with mass can. The speed of light is the universe's absolute limit, and it applies to everything: spaceships, radio signals, the influence of gravity, the spread of information itself. Here's where it gets philosophically weird though, and scholars still argue about the implications. Light doesn't experience time. From the perspective of a photon, if a photon could have a perspective, the journey from a distant star to your eye happens instantaneously. A photon leaving a galaxy 10 billion light years away would, from its own reference frame, arrive at your retina in the same moment it was created. The billions of years that pass are your experience, not light's. Light exists in a kind of eternal now, touching the moment of its birth and the moment of its absorption, as if they were the same point in space-time. This is the stuff that keeps cosmologists awake at night, which is ironic considering you're trying to sleep. But there's something almost soothing about it too. Right now, photons that have travelled for millions of years are landing on rooftops, on oceans, on the closed eyelids of sleeping children. They've crossed voids so empty that atoms are rare surprises. They've outlasted civilizations that rose and fell while they were in transit. And their journey ends quietly, absorbed by matter, their energy converted to gentle warmth. Every second, ancient light is arriving on Earth. Some of it will never be seen by anyone, landing in deserts or deep water where no telescope watches. Some of it has already passed us, continuing on into space, carrying information about stars to destinations that might not exist yet. Light is patient. Light is relentless. Light fills the universe with a web of travelling information, and you're sitting in the middle of it, receiving messages you didn't know were being sent. The light year, then, is a tribute to this constant traveller. By measuring distance in terms of light's journey, astronomers acknowledge that light is the only ruler long enough for cosmic scales. Kilometers are for continents. Light years are for the spaces between stars. And as you breathe slowly, watching the shadows shift almost imperceptibly on your ceiling, remember, the light making those shadows left the sun 8 minutes ago, carrying news of fusion reactions that already happened, warmth already generated before travelling 93 million miles just to fall softly across your face. Nothing goes faster than light. Nothing. It's not that we haven't found anything faster yet, or that current technology limits us, or that someday a clever engineer will build a ship that breaks the barrier. The speed of light is woven into the fabric of reality itself. It's less a speed limit and more a fundamental property of how the universe works, like saying nothing can be wetter than water or more circular than a circle. You might be wondering who enforces this rule. Is there some cosmic traffic cop pulling over photons and checking their velocity? The answer is stranger. The rule enforces itself, automatically and absolutely, through the mathematics of space-time. Einstein figured this out in 1905, and the universe has been quietly proving him right ever since. Albert Einstein was working as a patent clerk in Switzerland when he published his theory of special relativity. He was 26 years old, which is either inspiring or depressing, depending on how you feel about your own accomplishments at that age. The paper was titled "On the Electrodynamics of Moving Bodies," a name so boring it almost certainly guaranteed that nobody outside physics would ever read it. But inside those pages was a revolution that would reshape our understanding of space, time, and the impossibility of catching a light beam. Einstein started with a thought experiment. Imagine you're chasing a beam of light. You run faster and faster, approaching the speed of light yourself. What would you see if you caught up? Would the light freeze in front of you, hanging motionless in the air? This bothered Einstein deeply because Maxwell's equations, the mathematics governing electromagnetism, predicted that light should always move at the same speed regardless of how fast you're chasing it. There's no catching up. No matter how fast you go, light still races away from you at 299,792 kilometers per second. This seems impossible. If you're in a car going 60 miles per hour and another car passes you going 70, that car appears to be moving at only 10 miles per hour relative to you. Relative speeds add and subtract. That's how velocity works on highways and in everyday life. But light doesn't play by those rules. Light doesn't care how fast you're moving. Chase it at half the speed of light, and it still recedes at full speed. Chase it at 99% the speed of light, and it still recedes at full speed. The math makes no sense until you accept something uncomfortable. Space and time themselves are flexing to maintain light's constant velocity. This is special relativity. It tells us that as you approach the speed of light, time slows down for you relative to outside observers. Your clock ticks slower, your heartbeats take longer. From your perspective, everything feels normal, but if you looked back at Earth through a telescope, you'd see people moving in fast forward, aging years while you aged months. Space contracts too, squeezing in the direction of your travel so that distances appear shorter. The universe literally reshapes itself to prevent anything with mass from reaching light speed. And here's where it gets truly strange. To actually reach the speed of light, you would need infinite energy. As you accelerate, your relativistic mass increases, requiring more energy to accelerate further, which increases your mass more, requiring more energy, in a cycle that spirals toward infinity. You can get arbitrarily close, 99.9999999% of light speed, but that last fraction remains forever out of reach for anything that has mass. Photons, which are massless, get to travel at light speed from the moment they're created. They have no mass to accelerate, so they simply exist at maximum velocity, always and forever. Scholars still argue about whether there might be particles that travel faster than light without violating relativity. These hypothetical particles are called tachyons, and they would have to have imaginary mass, a concept that sounds like physics fan fiction, but is mathematically coherent. Tachyons, if they existed, could never slow down below light speed. They'd be trapped on the other side of the barrier, forever superluminal, unable to break down to normal speeds just as we're unable to accelerate up. Most physicists doubt tachyons exist, but the mathematics allows for them in a way that keeps the debate technically open. There's a quirky loophole though, and it keeps science fiction writers employed. Nothing can travel through space faster than light, but space itself can expand however fast it wants. During the very early universe, in the first fraction of a second after the Big Bang, space expanded faster than light could have travelled across it. Distant galaxies are currently receding from us faster than light speed, not because they're flying away, but because the space between us is stretching. They're not violating the speed limit. They're not moving through space quickly. The space itself is growing. It's a technicality that the universe exploits constantly, and it's why we can never reach certain parts of the cosmos no matter how long we wait or how fast we go. This has consequences for light years that most people never consider. When we say a galaxy is 10 billion light years away, we mean the light took 10 billion years to reach us. But during those 10 billion years, space expanded. The galaxy is now much farther than 10 billion light years. It's moved away while the light was travelling, like trying to swim toward a shore that keeps receding. The observable universe is about 93 billion light years across, even though it's only about 13.8 billion years old, because expansion has stretched everything while light was in transit. You're lying in a universe with a speed limit that nothing can break, in a space that itself ignores that limit by growing. Light races toward us at maximum velocity, and the source retreats just as fast in the other direction. Information travels, arrives, tells us stories about places that have since moved beyond our reach. The speed of light is simultaneously the fastest anything can go, and too slow to matter when cosmic expansion enters the picture. But tonight, none of that rushing applies to you. You're stationary, or nearly so, moving about 1,000 miles per hour as Earth rotates shore, and about 67,000 miles per hour as Earth orbits the Sun, and about 500,000 miles per hour as the Sun orbits the Milky Way centre. But locally, where it counts, where your body presses against whatever surface holds you, you're still. The speed limit doesn't constrain you because you're not trying to go anywhere. You're just here, resting, while light that has travelled unimaginable distances continues its ancient commute, some of it ending its journey on your skin, warming you with photons born in fusion reactions that finished before your species existed. The cosmic speed limit is absolute, and yet right now you don't need to go anywhere at all. Someone had to invent the light year. It didn't emerge naturally from the cosmos. No equation demanded it. Some frustrated astronomer, drowning in numbers too long to write and too large to imagine, finally threw down their quill and said, "Enough. We need a better way to measure this absurdity." The term light year first appeared in print in 1851, though the concept had been floating around scientific circles for a few years before that. A German astronomer named Otto Uli used it in a popular science article, trying to explain cosmic distances to regular people who had better things to do than count zeros. The word caught on because it had to. There was no alternative that didn't involve scientific notation stretching across entire pages. Before light years, astronomers tried everything. They measured distances in astronomical units, the distance from Earth to the Sun, about 93 million miles. This worked fine for the solar system. Jupiter is about 5 astronomical units from the Sun. Neptune is about 30. Pluto, when it was still considered a planet, sat at roughly 40. These are big numbers, but manageable ones. Your brain can at least pretend to grasp them if it squints. But step outside the solar system, and astronomical units become useless again. Proxima Centauri, our nearest stellar neighbour, is about 268,770 astronomical units away. That number is technically accurate and practically meaningless. It tells you nothing that you didn't already know, which is that stars are really, really far apart. Astronomers needed a bigger unit, something that could describe the gulf between suns without requiring a calculator and 3 cups of coffee. The light year was the answer, but it wasn't the only candidate. Around the same time, another unit was gaining traction, the parsec. The parsec is based on parallax, the apparent shift in a star's position when viewed from opposite sides of Earth's orbit. If you measure a star's position in January and again in July, when Earth has moved to the other side of the Sun, the star seems to have shifted slightly against the background of more distant stars. The amount of shift tells you how far away the star is. 1 parsec is the distance at which a star would show exactly 1 arc second of parallax, about 3.26 light years. Parsecs became the preferred unit in professional astronomy because they're directly tied to measurement techniques. When you calculate a star's distance from its parallax, the answer naturally comes out in parsecs. Light years require an extra conversion step. For working scientists, parsecs are more practical. For everyone else, light years are more intuitive. The general public has some sense of what a year feels like, even if they can't truly imagine light travelling for one. Nobody knows what an arc second feels like except perhaps extremely patient surveyors. There's a gentle ongoing debate about which unit is superior, and it occasionally gets heated in the way that only niche academic disagreements can. When the Hubble Space Telescope releases images of distant galaxies, press releases usually give distances in light years because journalists know their audience. Scientific papers use parsecs, or more often megaparsecs, millions of parsecs, because astronomers know theirs. It's not really a conflict so much as a translation issue between professionals and the public. Historians still argue about why the light year won the popular imagination. Part of it is simply the name. Light year sounds poetic, almost magical. It combines the fastest thing in the universe with the most fundamental unit of human time. Parsec sounds like something you'd order at a drive-thru. Han Solo's famous boast about making the Kessel Run in less than 12 parsecs was actually a unit error by the original screenwriters, who thought parsecs were a measure of time. Later films tried to retroactively justify it with increasingly tortured explanations about shortcuts through space. Sometimes mistakes become canon simply because enough people repeat them. The quirky truth about light years is that they connect 2 fundamentally different concepts: distance and time. No other common unit does this. A mile is just a mile, a kilometer is just a kilometer, but a light year carries temporal information baked into its definition. When you say something is 100 light years away, You're also saying that its light takes 100 years to reach you. Distance becomes duration. Space becomes time. The language itself encodes Einstein's insight that these things are related, that the universe doesn't really have separate space and time, but rather a unified space-time that light navigates at its maximum allowed pace. There's something almost philosophical about choosing to measure the cosmos in time. It acknowledges that distance at cosmic scales is less about space and more about when. When you look at a galaxy 1,000,000 light-years away, you're looking at 1,000,000 years ago. The where is inseparable from the when. If you could somehow teleport instantly to that galaxy, you'd find it changed, evolved, different from the image currently arriving at your telescope. The galaxy you see no longer exists. Only its light remains, a fossil of photons carrying information about a moment that has long since passed. The 19th century astronomers who popularized light years probably didn't think about all of this. They just needed a number that fit on a page and didn't induce immediate despair. They were pragmatists working with the tools available, trying to communicate about a universe that stubbornly resisted human comprehension. The light year was a compromise between scientific precision and psychological survival. It gave astronomers a way to speak about cosmic distances without each conversation becoming an exercise in existential crisis management. Today, light years are everywhere. Science fiction uses them constantly, sometimes correctly, sometimes not. News articles about exoplanets give distances in light years because the alternative is gibberish. Children learn about light years in school and nod as if they understand, which they don't, because nobody really does. The light year has become our default tool for thinking about the universe's size, even though the universe's size is fundamentally unthinkable. You're lying beneath a sky measured in light years. The nearest star system is about 4 of them away. The centre of our galaxy is about 26,000. The Andromeda galaxy is about 2.5 million. The edge of the observable universe is about 46 billion, though that number comes with enough caveats and expansions to fill its own sleepy podcast. Light years stack up, layer upon layer, distances that humans invented words for but will never truly feel. The tape measure is ready, the universe awaits, and the numbers are about to get much, much larger. Let's not leave home just yet. Before we venture to distant stars and galaxies that would make your calculator weep, let's take a moment to appreciate our own cosmic backyard. The solar system, the neighbourhood, the place where you pay rent, metaphorically speaking, on a small rocky planet orbiting an average yellow star. It feels cozy, doesn't it? Earth and the sun, the moon making its gentle rounds, a few neighbouring planets wandering through the night sky. Humans have been watching these celestial neighbours for thousands of years, naming them after gods, charting their movements, arguing about whether they influence our personalities based on when we were born. The solar system seems intimate, familiar, practically walkable if you had enough time and didn't need oxygen. It is not intimate, it is not walkable. The solar system is almost entirely empty space, with occasional specks of matter floating in it, pretending to be significant. Consider the distance from Earth to the Moon. It's about 384,400 kilometers, which sounds like a lot until you realize you could fit all the other planets in that gap with room to spare. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, line them up side by side, and they'd slip into the Earth-Moon gap like they were barely there. The Moon is close, cosmically speaking. It's the only celestial body humans have physically visited, and we've done it 6 times, which seems impressive until you remember that nobody's been back since 1972. More than 50 years of avoiding our nearest neighbour. We got the rocks we needed and apparently decided that was enough. Now let's talk about the Sun. It sits about 150 million kilometres from Earth, a distance that astronomers call 1 astronomical unit. Light covers this distance in approximately 8 minutes and 20 seconds. This means that if the sun suddenly vanished, not exploded, just vanished, like a cosmic magic trick, you wouldn't know for over 8 minutes. You'd go about your business, unaware that gravitational chaos was racing toward you at the speed of light. Then everything would become very interesting very quickly. The sun is so far away that its apparent size in our sky matches the moon's almost perfectly, despite the sun being about 400 times larger. This is a cosmic coincidence that makes total solar eclipses possible, where the moon exactly covers the sun's disk and reveals the corona. Historians still argue about whether ancient civilizations understood eclipses or simply feared them as divine signs. Probably both. The human response to a sky going dark in the middle of the day is rarely calm academic analysis. Beyond Earth's orbit, the distances start getting uncomfortable. Mars, at its closest approach, is about 55 million kilometers away, roughly a third of an astronomical unit. At its farthest, when it's on the opposite side of the Sun, Mars sits about 400 million kilometers distant. These variations are why Mars missions have launch windows, brief periods when the geometry is favourable. Miss the window, and you wait another 2 years for the planets to align again. Space travel, it turns out, requires patience bordering on Buddhist. Jupiter lurks at about 5 astronomical units from the Sun. It's the giant of our system, containing more mass than all other planets combined, and it takes light about 43 minutes to travel from the Sun to its turbulent cloud tops. Saturn, with its famous rings, orbits at nearly 10 astronomical units. Light takes about an hour and 20 minutes to reach it. When you look at Saturn through a telescope, you're seeing it as it was roughly an hour and a half ago. Not ancient history, but not the present either. Just slightly delayed, like a streaming video buffering very slowly. The outer planets push the boundaries further. Uranus sits at about 20 astronomical units, Neptune at 30. Light takes over 4 hours to reach Neptune from the Sun. Voyager 2, the only spacecraft to visit both ice giants, took 12 years to reach Uranus and another 3 to reach Neptune. It was launched in 1977 and is still sending back data from beyond the solar system, though at this point its signal is so weak that receiving stations need antennas the size of football fields to hear it. And then there's the Kuiper Belt, the ring of icy debris beyond Neptune where Pluto and its fellow dwarf planets live. Pluto's orbit is highly elliptical, ranging from about 30 to 50 astronomical units from the Sun. At that distance, sunlight takes over 5 hours to arrive, and the Sun appears not as a blazing disk but as an extremely bright star. You could still read by it technically, but you'd need to squint. New Horizons reached Pluto in 2015 after a 9-year journey, sent back stunning images of mountains and glaciers made of frozen nitrogen, and then continued on into the dark. Here's the terrifying part. The solar system is mostly empty. If you shrunk the Sun down to the size of a white blood cell, the Kuiper Belt would be about 4 inches away. The entire known solar system at that scale would fit in your hand, and in that hand-sized space, the planets would be essentially invisible, microscopic dots separated by relatively vast distances of nothing. The solar system is not a crowded neighbourhood. It's a few pebbles scattered across a desert. Beyond the Kuiper Belt lies the Oort cloud, a theoretical shell of icy objects extending perhaps 2 light-years from the Sun. We've never directly observed it, but comets with extremely long orbits suggest it exists, a sparse halo of frozen debris left over from the solar system's formation. If the Oort cloud is real, and most astronomers believe it is, then our solar system's true boundary is vastly larger than textbook diagrams suggest. The Sun's gravitational influence reaches outward for nearly half the distance to the nearest star. You live in a cosmic territory that takes light years to cross. Your home isn't just Earth, or even the inner solar system. It's a bubble of space surrounding an ordinary star, a bubble so large that no human has ever come close to its edge, a bubble so empty that spacecraft can travel through it for decades without bumping into anything substantial. This is your neighbourhood. This is where you belong. And it is almost entirely nothing. The sun rose this morning as it always does, flooding your corner of the planet with light and warmth. Except it didn't. Not really. The sun finished rising about 8 minutes before you noticed. The light that painted your walls, that warmed your skin, that convinced your sleepy body to accept consciousness. That light was already old when it arrived. 8 minutes and 20 seconds old, to be specific. Ancient by photon standards, though admittedly brief by yours. This is one of those facts that sounds simple, but unravels strangely the longer you think about it. The sun you see is never the sun as it is. It's always the sun as it was, 8 minutes and 20 seconds ago. If someone invented a magical instant camera that could photograph the sun in real time, the image would look different from what your eyes perceive. Slightly different. Probably imperceptibly so, but different nonetheless. Solar flares that erupted 8 minutes ago haven't reached your vision yet. Sunspots that formed or faded in those 8 minutes remain invisible until their light completes the journey. 8 minutes doesn't seem like much. It's barely enough time to make coffee. But consider what those 8 minutes represent. 93 million miles of travel at the fastest possible speed in the universe. Light, actual light, the speediest thing that exists, needs almost 10 minutes to cover the distance between the sun and your eyeball, and that's the closest star, the one right next to us, the one we literally orbit. The light leaving the sun right now will arrive at Earth around the time you might glance at a clock and wonder where the morning went. If you look directly at the sun, don't. You'd be seeing it as it was before you finish brushing your teeth. Time dilation at cosmic distances is disorienting because it forces you to acknowledge that now is a local concept. Your now and the sun's now never quite sync up. There's always a gap, always a delay, always a version of reality that hasn't reached you yet. This 8-minute delay was one of the first cosmic time lags humans calculated accurately. Danish astronomer Ole Rømer, the same one who measured light speed using Jupiter's moons, figured out in the 17th century that light wasn't instantaneous. Before Rømer, many scientists assumed light travelled infinitely fast, that when the sun shone, its light reached Earth at the exact moment it was emitted. Rømer's observations proved otherwise, and suddenly the universe got bigger and stranger. Light had a speed. Distance meant delay. The present was always slightly out of reach. Scholars still argue about when humans first intuitively grasped that starlight was old. Ancient astronomers tracked stars meticulously, but likely didn't consider that they were seeing the past. The concept requires understanding that light travels and that space is vast, both ideas that took millennia to develop. Some historians suggest that medieval Islamic astronomers may have suspected light had a finite speed, but the evidence is fragmentary. What we know for certain is that the modern understanding of cosmic time delay is barely a few centuries old, a blink in human history. Here's a quirky thought experiment. Imagine the sun vanished, just disappeared, right at this moment. You wouldn't know. For 8 minutes and 20 seconds, everything would seem normal. The sky would remain bright. Plants would photosynthesize. Birds would chirp. The day would continue as usual. Then, 8 minutes later, two things would happen simultaneously. The sky would go dark as the last of the sunlight arrived with nothing behind it. And Earth would begin drifting off course, freed from the sun's gravitational pull, which also travels at the speed of light. Gravity, it turns out, has the same speed limit as electromagnetic radiation. The universe is consistent in its restrictions, even if those restrictions are inconvenient. For 8 minutes, you'd live in a world that no longer existed. A world lit by a dead star, held in orbit by a vanished mass, utterly unaware of the catastrophe already racing toward it. This is what it means to see the past. You're always, in every moment, looking at things as they were, not as they are. Usually the delay is negligible. Light from your lamp reaches your eye in nanoseconds. The delay shorter than any human sense could detect. But extend the distance, and the delay becomes unavoidable. The moon's light takes about 1.3 seconds to reach you. Mars at its closest delays about 3 minutes. Jupiter's light is over half an hour old by the time you see it. Saturn's over an hour. Pluto's about 5 hours. You're surrounded by a solar system that exists in layers of time, each planet showing you a different moment in its own past, all of them out of sync with your present, none of them quite real. And here's the comforting part. If you're in the mood for comfort, this delay doesn't matter for anything you're likely to do. You don't need real-time information about the sun. The 8-minute lag is cosmically significant but practically irrelevant. By the time the sun's light reaches you, the sun hasn't changed in any way you'd notice. It's been fusing hydrogen for 4.6 billion years and will continue for another 5 billion. 8 minutes of delay barely registers against that timescale. This sun you see is, for all practical purposes, the sun that exists. The gap is there, but it doesn't hurt you. Tonight, as you drift towards sleep, you're seeing starlight that has travelled for years, centuries, millennia. The sun's 8-minute delay was just the beginning, a gentle introduction to the idea that looking up is looking back. The stars above you are time capsules, each one a message from its own distant past, arriving at your eyes on schedules determined by unimaginable distances. Some of that light left its source before humans existed. Some of it has been travelling since before Earth formed. You're bathing in ancient light right now. The universe's past is gently touching your face. And somewhere out there, light that left your planet today is beginning a journey that will take it past every star you can see, toward destinations it won't reach for thousands, millions, billions of years. Everything is delay, everything is old, everything is beautifully quietly out of date. Now that you understand sunlight takes 8 minutes to reach you, let's make things worse. Let's visit the nearest star beyond our sun and discover just how cruel the word nearest can be when applied to cosmic distances. Her name is Proxima Centauri, and she's a red dwarf about 4.24 light-years from Earth. That makes her our closest stellar neighbour, the sun's nearest cosmic companion, the most accessible star in the entire universe after our own. If interstellar travel ever becomes possible, Proxima Centauri will almost certainly be our first destination. She's the obvious choice, the beginner's level, the tutorial stage of galactic exploration. She might as well be on the other side of eternity. 4.24 light-years translates to roughly 40 trillion kilometers. If you drove a car at highway speeds without stopping, no gas breaks, no bathroom breaks, no existential crises, you'd arrive at Proxima Centauri in about 50 million years. The Voyager 1 spacecraft, currently the fastest object humans have ever sent into space, would take about 70,000 years to cover the distance, though it's not actually heading in that direction. If it were, your great-great-great times 1,000 grandchildren might receive a postcard from the vicinity. This is what nearest means in cosmic terms. The closest star is so far away that no human who has ever lived would survive the journey using any technology we've invented. The word close becomes a joke, a lie, a cruel irony that astronomers apparently find amusing. Proxima Centauri is close the way Antarctica is close to your kitchen. Technically on the same planet, practically unreachable on foot. Proxima Centauri isn't alone out there. She's part of a triple star system called Alpha Centauri, which sounds like a science fiction setting because it basically is. The system includes Alpha Centauri A, and Alpha Centauri b, two Sun-like stars that orbit each other, plus Proxima Centauri, a smaller red dwarf that orbits the pair at a much greater distance. Proxima's orbit takes about 550,000 years to complete, meaning she's barely moved since the first humans walked upright. By cosmic standards, she's right next door. By human standards, she's unfathomably far. In 2016, astronomers discovered a planet orbiting Proxima Centauri. They named it Proxima Centauri b, following the convention of naming exoplanets, with letters in order of discovery. Proxima b sits in its star's habitable zone, the region where liquid water could theoretically exist on a planet's surface. This makes it one of the most tantalizing targets in the search for extraterrestrial life. A potentially habitable planet orbiting the closest star to our Sun. It sounds like the universe is teasing us, dangling a prize just slightly out of reach. But there are complications. Red dwarfs like Proxima Centauri are temperamental. They emit powerful flares that could strip away a planet's atmosphere and irradiate its surface. Proxima b is also tidally locked, meaning one side permanently faces its star while the other side is locked in eternal darkness. Life might exist in the twilight zone between the two hemispheres, but conditions wouldn't be anything like Earth. Scholars still argue about whether Proxima b could harbour life, or whether it's a scorched rock circling a volatile star. We won't know for certain without sending probes, and probes take a very, very long time. Here's a quirky detail about Proxima Centauri. She wasn't discovered until 1915. Despite being the closest star to our Sun, she's too dim to see with the naked eye. You could spend your entire life staring at the night sky and never notice her. Robert Innes, a Scottish astronomer working in South Africa, found her while comparing photographic plates. She'd been there all along, our nearest neighbour, invisible and unknown, patiently waiting for someone to point a telescope in the right direction. The light leaving Proxima Centauri right now won't reach Earth until sometime around 2029. If Proxima Centauri exploded today, which she won't, red dwarfs don't work that way. We'd have no idea for more than 4 years. By the time the light arrived, whatever had happened would be ancient history by stellar standards. We'd be watching a movie that finished filming before the pandemic started. Several projects are attempting to bridge the gap to Proxima Centauri, at least virtually. Breakthrough Starshot, funded by billionaire Yuri Milner, proposes sending tiny spacecraft propelled by powerful laser beams to the Alpha Centauri system. These starships would be about the size of postage stamps and could theoretically reach 20% of light speed, making the journey in roughly 20 years. It's ambitious, possibly impossible, and exactly the kind of audacious idea that sometimes works. Even if it succeeds, the starships couldn't slow down. They'd flash past the system in moments, taking photos as they went, then continue into interstellar space forever. You might wonder why anyone bothers. If Proxima Centauri is so far away, if reaching it is so impractical, why do astronomers care about a star nobody will ever visit? The answer, like most good answers, is complicated. We care because it's there. We care because humans have always explored, always pushed outward, always wanted to know what lies beyond the next horizon, even when reaching that horizon was impossible. We care because the alternative, accepting that the universe is too large for us, giving up on ever knowing our neighbours, feels like a kind of death. And we care because Proxima Centauri is the first step. If we can ever develop technology to reach the nearest star, the next step becomes possible, and the next, and the next. The galaxy opens up slowly, star by star, light year by light year. Proxima Centauri isn't a destination, she's a threshold. She's the door we haven't figured out how to open yet. You're lying on a small planet warmed by a small star surrounded by emptiness that stretches 4.24 light years to the nearest neighbour. That neighbour is too far to visit, too dim to see, too hostile to welcome us warmly. And yet, she's there. Proxima Centauri, the closest star. The first step into a universe so large that even this tiny first step would take generations to complete. The door remains closed, but at least we know where it is. Now let's do something unsettling. Let's talk about how the stars you see tonight might not exist anymore. You've probably heard this fact before, tossed around at parties by someone trying to sound deep. Some of those stars are already dead, but their light is still travelling to us. It's become a cliché, the kind of cosmic poetry that sounds profound without requiring actual understanding. But the cliché's true, and understanding it properly changes how you look at the sky. When you see a star, you're not seeing the star, you're seeing light that left the star some time ago, years, centuries, millennia, depending on the star's distance. That light has been travelling through the void, utterly indifferent to what happened to its source after departure. The star could have exploded, collapsed, transformed into something unrecognisable, and the light would keep coming, oblivious, carrying information about a moment that no longer exists. Take Betelgeuse, the red supergiant in Orion's shoulder. It's about 700 light-years away, though estimates vary. The light reaching your eyes tonight left Betelgeuse around the year 1325, give or take. That's before the Black Death swept through Europe, before the Renaissance, before Columbus crossed the Atlantic. Medieval peasants could have watched this same light beginning its journey had they known to look. By the time it arrived at your retina tonight, everything they knew has turned to dust. Betelgeuse is expected to explode as a supernova sometime in the next 100,000 years or so. That's a geological blink, but a human eternity. When it finally detonates, the explosion will be visible during the day, bright enough to cast shadows, spectacular enough to terrify anyone who doesn't understand what they're seeing. But here's the twist. Betelgeuse might have already exploded. The light from the explosion could be travelling toward us right now, 700 years into its journey, with 700 more to go. We'd have no way of knowing until it arrived. The sky holds its secrets until light reveals them. Not every star you see is a corpse waiting to be discovered. Most stars are stable, burning steadily through their hydrogen supplies on timescales of billions of years. The Sun has another 5 billion years of life. Stars smaller than the Sun last even longer. Red dwarfs can burn for trillions of years, longer than the current age of the universe. The night sky is full of survivors, stars that were shining before Earth formed and will keep shining long after Earth is gone. But massive stars live fast and die young. They burn through their fuel in millions of years rather than billions, then collapse dramatically. A significant fraction of the bright stars you can see without a telescope are these massive, short-lived types. Their brilliance makes them visible across vast distances, but that brilliance comes at a cost. Stars like Rigel, Deneb and Polaris are all cosmically temporary, destined to end in explosions or collapses within the next few million years. Astronomically speaking, they're already walking dead. Scholars still argue about how many visible stars have already died. The calculations depend on stellar distances, lifespans, and explosion probabilities, all of which carry uncertainties. Most estimates suggest that at least a few of the stars visible to the naked eye have likely ended, their deaths unannounced because the messengers haven't arrived yet. It's impossible to know which ones. The sky doesn't label its ghosts. Here's a quirky detail that complicates things. We can sometimes detect a star's death before we see it. Neutrinos, nearly massless particles produced in enormous quantities during supernovae, travel slightly faster than light through the collapsing star's outer layers. In 1987, neutrino detectors registered a burst about 3 hours before the supernova in the Large Magellanic Cloud became visible. The neutrinos arrived first, heralds of a catastrophe that light was still catching up to. For a few hours, scientists knew a star had died before they could see the evidence. The stars you see are time capsules. Each one shows you a different moment in the past, none synchronized with your present, all delayed by their distance from Earth. Sirius, the brightest star in the night sky, is only 8.6 light-years away. You're seeing it as it was about 8.5 years ago. Polaris, the North Star, is about 400 light-years distant. Its light left around the time Galileo was pointing his first telescope at the heavens. The Andromeda galaxy, visible as a smudge to the naked eye on dark nights, is 2.5 million light-years away. You're seeing it as it was when early humans were just learning to chip stone tools. Looking at the night sky is archaeology. Every photon is a fossil, carrying information about a moment that ended long before it arrived. You're not seeing the universe, you're seeing the universe's history, a layered record of past moments delivered at the speed of the light. The present exists out there, somewhere, but you'll never see it. By the time its light reaches you, it will already be the past. This should be disturbing, but somehow it's not. Maybe because it doesn't change anything practical. The stars still guide sailors and romantics. The constellations still mark the seasons. Whether Betelgeuse exploded yesterday or will explode in 100,000 years, Orion still rises in winter, still dominates the southern sky, still looks exactly as it did to every human who ever tilted their head back and wondered. The sky's a museum, and you have free admission every night. The exhibits change slowly, imperceptibly, on timescales no human life can track. What you see is not what exists, but it's what you get. It's all anyone has ever gotten. Every poet, every scientist, every child afraid of the dark has looked up at the same delayed, fossilized light and seen the same impossible past pretending to be the present. Tonight you join them. You look up, or imagine looking up as your eyes drift closed, and you see ghosts and survivors mixed together, indistinguishable, all of them beautiful, all of them far, all of them telling you stories that ended before the stories arrived. Some of those stars are already dead. You're seeing them anyway. Let's pull back, way back. So far back that individual stars dissolve into a haze, a glow, a river of light smeared across the sky. That river has a name you've heard since childhood, a name so familiar it's easy to forget what it actually means. The Milky Way. You live inside the Milky Way. You're a passenger on a small planet orbiting a medium star in a spiral arm of a galaxy containing somewhere between 100 billion and 400 billion stars. The range is uncertain because nobody has actually counted them. Astronomers estimate based on brightness and mass, and their estimates vary by a factor of 4, somewhere between 100 billion and 400 billion. That's the precision we're working with. Give or take a few hundred billion stars, the Milky Way stretches about 100,000 light-years from edge to edge. Let that sink in. Light, the fastest thing in the universe, would need 100,000 years to cross our galaxy. When you look at a star on the far side of the Milky Way, assuming you could see one directly, you're seeing light that left around the time modern humans were just migrating out of Africa. The galaxy is so vast that its own internal communications take geological epochs to deliver. Our solar system sits about 26,000 light-years from the galactic center. That's the middle of nowhere, cosmically speaking. Neither at the bustling core nor at the sparse outer edges, just an unremarkable neighborhood in an unremarkable spiral arm called the Orion Spur. The center of the galaxy is hidden from direct view by enormous clouds of gas and dust, but infrared and radio telescopes can peer through the veil. What they find there is spectacular and terrifying. Millions of stars packed impossibly close, orbiting a supermassive black hole called Sagittarius A star that weighs about 4 million times as much as the Sun. Stars near the galactic center are separated by fractions of light-years rather than full ones. Imagine a night sky blazing with thousands of stars as bright as Venus, so many that true darkness never comes. The Milky Way's core is a cosmic downtown, dense and dangerous and beautiful. The supermassive black hole at its heart doesn't actively swallow stars very often. It's surprisingly well behaved for something so massive, but its gravity shapes everything around it. Stars orbit the black hole at tremendous speeds, completing orbits in years rather than the millions of years our sun takes to circle the galaxy. Out here in the suburbs, things are quieter. The nearest star to the sun is over 4 light-years away. The next nearest is a bit farther. The neighbourhood is spacious, almost lonely. If intelligent life exists elsewhere in the galaxy, the distances ensure that conversation would be impractical. A message sent at the speed of light to even a nearby star would take years to arrive, and years more for a reply. The galaxy is too large for chat, too spread out for community. Everyone who might exist out there is isolated by light years, separated by gulfs that communication can bridge only slowly, if at all. Scholars still argue about the Milky Way's exact structure. We can't exactly step outside and take a picture. Everything we know about our galaxy's shape comes from mapping stars, measuring distances and inferring structure from patterns. The consensus is that the Milky Way is a barred spiral, with a central bar-shaped structure and several curved arms spiralling outward. But the details are fuzzy. How many arms? Where exactly are they? How tightly wound? These questions have different answers depending on which astronomer you ask and which data they trust. Here's a quirky fact about the Milky Way. It's not holding still. The entire galaxy is rotating, and our solar system completes one orbit around the galactic centre roughly every 225 million years. This period is sometimes called a galactic year. In the time since the Sun and Earth formed, about 4.6 billion years ago, we've completed only about 20 galactic orbits. Dinosaurs went extinct about 65 million years ago, which is less than a third of a galactic year. The Sun has barely moved, galactically speaking, since the Cretaceous ended, and the Milky Way itself is moving. It's drifting through intergalactic space at about 2.1 million kilometers per hour, pulled by the gravity of the Andromeda galaxy and a region of concentrated mass called the Great Attractor. Everything is in motion. Planets around stars, stars around galaxies, galaxies toward each other and toward mysterious gravitational centers beyond. The universe has no fixed points, no stationary reference frame. Stillness is an illusion born of scale. You feel motionless right now, but you're spinning with Earth's rotation, orbiting with Earth around the Sun, circling with the Sun around the galaxy, and hurtling with the galaxy toward destinations unknown. The Milky Way is also slowly consuming smaller galaxies. We're currently digesting at least 2 dwarf galaxies, the Sagittarius Dwarf Elliptical Galaxy and the Canis Major Dwarf Galaxy, which the Milky Way's gravity is tearing apart and absorbing. These are not violent collisions, but slow gravitational mergers, streams of stars being pulled into new orbits over millions of years. The Milky Way grew large by eating smaller companions, and it will continue to eat until something larger eats it. That something larger is Andromeda, which is heading our way, but we'll get to that later. For now, sit with the size of your home galaxy, 100,000 light-years across, hundreds of billions of stars, a supermassive black hole at the centre, spiral arms stretching outward like a slow-motion pinwheel, and you on a small planet in an ordinary solar system about 2/3 of the way out from the centre, seeing only the tiniest fraction of your galactic neighbours, most of them too faint or too far to detect with your unaided eyes. The Milky Way is home. It's also impossibly, incomprehensibly large. Every star you've ever seen belongs to this one galaxy. Everything humanity has ever known, ever reached, ever imagined reaching exists in one small corner of this spiral structure. The Milky Way is the whole world for any light-speed-limited civilization, a universe unto itself, a prison made of distance, and it's just one galaxy among trillions. There's another galaxy coming toward us, and it's been coming for a very long time. Her name is Andromeda, and she's beautiful, and she's absolutely going to collide with our home. Don't panic, the collision won't happen for about 4 billion years. By then, the Sun will have burned through most of its hydrogen and begun its transformation into a red giant, making the whole galaxy collision situation somewhat moot for anyone living on Earth. Also, collision is a misleading word. Galaxies don't crash together like cars in an intersection. They're mostly empty space, remember? When galaxies collide, they pass through each other like ghosts, their stars almost never actually touching. The gravity interacts, the shapes distort, stars get flung into new orbits, but individual stellar systems remain intact, separated by light years of emptiness too vast for actual impact. Andromeda sits about 2.5 million light-years away. That makes her the most distant object you can see with the naked eye, a faint smudge in the constellation Andromeda, visible on dark, clear nights if you know where to look. Everything else you see unaided belongs to the Milky Way. Andromeda is the exception, the one extra-galactic visitor in your field of view, the one object that proves galaxies other than our own exist. The light reaching your eyes from Andromeda left about 2.5 million years ago, when our ancestors were still figuring out stone tools and fire. When you look at Andromeda, you're seeing it as it was during the Paleolithic era. Homo erectus might have looked up at the same smudge, not knowing what it was, seeing the same ancient light that's arriving tonight. The photons don't care who receives them. They've been travelling since before humans were recognisably human. Andromeda is larger than the Milky Way. She contains roughly 1 trillion stars compared to our few hundred billion. Her disk stretches about 220,000 light-years across, more than twice the diameter of our galaxy. When the collision finally happens, the smaller Milky Way will likely be absorbed into the larger Andromeda, creating a new elliptical galaxy that some astronomers have already named Milkomeda. The name is terrible. The event will be spectacular if anyone with the ability to appreciate spectacle still exists to watch. The two galaxies are approaching each other at about 400,000 kilometers per hour. This sounds fast, and it is, roughly 10 times the speed of a typical meteor. But across 2.5 million light-years, even this velocity requires billions of years to close the gap. The universe operates on timescales that make human urgency seem quaint. We panic about deadlines measured in hours. Galaxies have collisions scheduled for eons from now, and are in no particular hurry. Scholars still argue about the exact timeline and outcome of the collision. Computer simulations suggest the galaxies will pass through each other at least once, possibly twice, before finally merging. Each pass will distort both galaxies, flinging stars into enormous tidal tails, triggering bursts of star formation as gas clouds compress. The night sky of any planet that survives will be transformed. Instead of a gentle milky band, the sky might show dramatic streamers of stars, close encounters with globular clusters, and the brilliant chaos of two galaxies intertwining. Here's a quirky detail. The collision has technically already begun. The Milky Way and Andromeda are connected by a faint bridge of intergalactic gas, the first tentative tendrils of gravitational interaction. The halos of dark matter surrounding each galaxy likely overlap already. What seems like a distant future event is, in some ways, already underway. The two galaxies are shaking hands across the void, preparing for an embrace that will last hundreds of millions of years. Andromeda was the first galaxy confirmed to be outside the Milky Way. For centuries, astronomers argued about whether spiral nebulae like Andromeda or independent galaxies, or simply clouds of gas within our own. The debate was settled in 1924 by Edwin Hubble, who identified Cepheid variable stars in Andromeda and used them to calculate a distance far beyond the Milky Way's boundaries. In one stroke, Hubble expanded the known universe from a single galaxy to an indefinite number of galaxies, each separated by unfathomable distances. Andromeda was the proof that we were not alone, that the universe contained more than just us, that the cosmos was larger than anyone had imagined. You might wonder how we know Andromeda is approaching when everything else in the universe seems to be moving away. The answer is gravity. On cosmic scales, the expansion of space carries galaxies apart, but gravity can overcome this expansion locally. The Milky Way and Andromeda are part of a small group of galaxies called the local group, bound together by mutual attraction. While distant galaxies rush away from us faster than light speed, our nearest neighbours are actually falling toward us, pulled by the same force that keeps your feet on the floor. The local group contains more than 80 known galaxies, most of them small dwarfs orbiting the two big spirals. Andromeda has its own collection of satellite galaxies, just as the Milky Way has the large and small Magellanic Clouds. It's a family of galaxies, a gravitationally bound neighbourhood in a universe that is otherwise flying apart. When Andromeda and the Milky Way merge, the rest of the local group will eventually follow, accumulating into one enormous elliptical galaxy that will persist for trillions of years. Andromeda is coming. She's been coming since before Earth existed, moving steadily closer while light years slowly close. When you look at her tonight, that faint smudge, that distant glow, you're seeing your future. Not your personal future, certainly, but the future of everything that has ever happened in the Milky Way. Every star you've ever seen will someday orbit in a galaxy shaped by Andromeda's gravity. The constellations will dissolve. The familiar patterns will scatter. Something new will emerge, something no human will ever see. Something wonderful and alien and utterly beyond our reach. But that's billions of years away. Tonight, Andromeda is just a smudge, a beautiful, ancient, approaching smudge, carrying 1 trillion stars toward a rendezvous with your home. Sleep well. Just when you thought you had a handle on things. 2 galaxies, a few 100 billion stars each, a collision scheduled for 4 billion years from now. The universe reminds you that it is, in fact, ridiculous. Galaxies don't float alone. They clump together into clusters, and clusters clump into superclusters, and superclusters form filaments that stretch across billions of light years, creating a cosmic web so vast that individual galaxies become mere pixels in an image too large to render. The Milky Way and Andromeda belong to the local group, which contains over 80 galaxies spread across about 10 million light years. That sounds enormous, until you learn that the local group is just a small outlying part of the Virgo cluster, which contains over 1,000 galaxies spread across about 15 million light years. The Virgo cluster is the nearest large galaxy cluster to us, a gravitational metropolis compared to our rural local group. Looking at the Virgo cluster, you're seeing a city of galaxies, each one containing billions of stars, all bound together by gravity into a structure that takes light millions of years to cross. But wait, there's more. The Virgo cluster is itself just a component of the Virgo supercluster, sometimes called the local supercluster, which contains at least 100 galaxy groups and clusters spread across about 100 million light years. The Milky Way is a suburb of a suburb, a tiny town on the outskirts of a metropolitan area that would take light 100 million years to cross if light could cross it, which it can't, because space is expanding and the far side is receding faster than light can travel. And even the Virgo supercluster is just a small part of something larger, the Laniakea supercluster. Laniakea, a name meaning immense heaven in Hawaiian, was identified in 2014 when astronomers mapped the gravitational flows that link galaxy clusters together. Laniakea contains over 100,000 large galaxies and possibly millions of smaller ones, spread across about 500 million light-years. All of these galaxies are flowing toward a common gravitational center called the Great Attractor, a region of concentrated mass that nobody fully understands. The Great Attractor is one of those cosmic mysteries that makes astronomers squint and mutter. It's located about 200 million light-years away, in the direction of the constellation Centaurus, hidden behind the dense stars and dust of the Milky Way's disk. We can't see it directly, the Milky Way blocks the view, but we can measure its gravitational influence. Hundreds of thousands of galaxies, including ours, are being pulled toward it. Something massive lurks there, perhaps a huge concentration of galaxy clusters, perhaps something stranger. Scholars still argue about its exact nature, but they agree it's real, and it's pulling us at about 2 million kilometers per hour. Here's a quirky fact about galaxy clusters. When they collide, the results are among the most energetic events in the universe. Galaxy cluster collisions release more energy than any other cosmic phenomenon except the Big Bang itself. The Bullet Cluster, located about 3.8 billion light-years away, is the result of two clusters smashing through each other. Observations of the Bullet Cluster provided some of the strongest evidence for dark matter. The visible matter, mostly hot gas, behaves differently from the invisible mass, dark matter, and their separation during the collision revealed what couldn't be seen directly. Dark matter is another cosmic mystery woven through every structure at this scale. Galaxy clusters are held together by gravity, but the visible matter, stars, gas, dust, isn't massive enough to account for the gravitational pull observed. There must be additional mass, invisible mass, matter that doesn't interact with light, but does interact with gravity. This dark matter outweighs ordinary matter by about 5-1. When you look at a galaxy cluster, you're seeing the visible frosting on an invisible cake. The cake is what actually holds everything together. The cosmic web extends beyond superclusters. When astronomers map the universe at the larger scales, they find that galaxies and clusters are distributed in filaments and walls surrounding enormous voids. These voids are not truly empty, they contain sparse galaxies and thin gas, but compared to the dense filaments, they might as well be. The largest known voids are over 1 billion light-years across. Light could travel through these regions for 1 billion years and encounter almost nothing. You exist on a small planet, in a medium solar system, in an average galaxy, in a small group of galaxies, in a large cluster of groups, in an enormous supercluster of clusters, connected by filaments to other superclusters in a web that stretches across the observable universe. And every level of this hierarchy is separated by distances measured in millions, hundreds of millions, billions of light years. The numbers have stopped meaning much, haven't they? That's normal. Human brains evolved to navigate African savannas, not to comprehend cosmic webs. 1 million light-years is too large to feel, so your mind files it next to infinity and moves on. The difference between 100 million light-years and 1 billion light-years barely registers. They're both really far, effectively infinite, beyond practical consideration. But here's the thing, it's real, all of it. The clusters and superclusters and filaments aren't metaphors or approximations or fantasies dreamed up by astronomers who need to justify their grants. They're out there right now, existing in exactly the configurations mapped by telescopes and simulations. The universe is this large, the structures are this vast, you are this small. That's not meant to be depressing. It can be, if you let it. But it can also be astonishing, humbling, even peaceful. You're part of something so large that your problems cannot possibly matter to it. The Virgo supercluster doesn't care about your deadlines, your anxieties, your regrets. It's too big to care. And in that bigness, there might be a kind of freedom. Your struggles are real and important to you, but they're not cosmic. The universe will continue regardless. Galaxies will cluster and superclusters will flow toward the great attractor, whether or not you finish that project on time. The universe is ridiculous. It's okay to be small within it. There's a boundary to what we can see. Not a wall, not a physical barrier, but a horizon beyond which light has not had time to reach us since the universe began. This is the observable universe, and it stretches about 46 billion light-years in every direction, creating a sphere of visibility 93 billion light-years across. Wait, the universe is only about 13.8 billion years old. How can we see things 46 billion light-years away? If light travels at a fixed speed, shouldn't the farthest things we can see be exactly 13.8 billion light-years distant? The answer is expansion, and it will hurt your head if you think about it too hard. Space itself is stretching. It has been stretching since the Big Bang, and it continues to stretch today. When light left a distant galaxy billions of years ago, that galaxy was much closer than it is now. The light travelled toward us at its constant speed. But while it travelled, space expanded, carrying both the light and its source farther apart. By the time the light arrives, the galaxy has moved, not because it's flying through space, but because the space between us has grown. The oldest light we can detect is the cosmic microwave background, which we'll discuss later. That light has been travelling for about 13.8 billion years, but the region that emitted it is now about 46 billion light-years away due to expansion. Everything in the observable universe is farther than its light travel time suggests, because everything has been receding while the light was en route. The observable universe contains roughly 2 trillion galaxies, according to recent estimates. That number used to be about 200 billion, but improved telescopes and better analysis revealed that many faint small galaxies had been missed. 2 trillion galaxies, each containing billions or trillions of stars, each star potentially hosting planets, all spread across 93 billion light-years of observable space. The numbers become prayers at this scale, mantras repeated to convey magnitude without genuine comprehension. But here's what really twists the mind. The observable universe is probably just a tiny fraction of the entire universe. Beyond the observable horizon, space almost certainly continues. There's no reason to think the universe ends at the edge of our visibility. The Big Bang happened everywhere, not at a single point, and space likely extends far beyond what we can see. Some cosmological models suggest the universe is infinite, stretching forever in every direction, containing an infinite number of galaxies, an infinite number of stars, an infinite number of planets. Other models suggest the universe is finite but unbounded, curved back on itself like the surface of a higher dimensional sphere, so that if you travelled in one direction long enough, you'd eventually return to where you started. Scholars still argue about the universe's true size and shape. We don't know. We can't know, not with current physics, because the information we'd need is beyond our light horizon. The universe could be 100 times larger than what we see, or 1 billion times larger, or infinite. The observable universe is our prison of perspective, our bubble of light, our limited view into something vastly bigger. Here's a quirky detail. The edge of the observable universe isn't in any particular direction. It's at the same distance in every direction. You are the center of your observable universe, not because you're cosmically special, but because the observable universe is defined by what light has had time to reach you. Someone in the Andromeda galaxy has a different observable universe, shifted by 2.5 million light-years in our direction. Their horizon excludes some galaxies we can see and includes some we cannot. There's no universal edge, just individual bubbles of visibility, billions of them, each centered on its observer. The observable universe is expanding too, but not fast enough. Here's the cruel irony. Space is stretching faster than our observable horizon can grow. Galaxies currently on our horizon are receding faster than light, not through space, but with space as it expands. We will never receive any more light from them. They're leaving our observable universe forever, crossing the horizon into a region we can never access. Every second, galaxies slip beyond our ability to ever see, know, or contact. The universe is getting darker, lonelier, as expansion accelerates, and more of creation vanishes behind the horizon. In the far future, trillions of years from now, the observable universe for any given observer will contain only its local galaxy cluster, probably the merged remnant of the local group, surrounded by utter emptiness. Everything else will have receded beyond visibility. Future civilizations, if any exist, might never know that other galaxies exist. They'll look at their sky and see nothing but their own stars, with no evidence that the cosmos extends beyond their isolated island. The universe will have erased itself from their awareness. You live in a privileged era. Right now, the universe is still young enough that we can see its structure, its history, its vastness. We can map galaxy clusters billions of light years away. We can detect the cosmic microwave background and glimpse the universe's infancy. We can know, at least approximately, how big and old and strange everything is. Future beings might not have that luxury. They might be born into a universe that looks small and lonely, with no way to know what lies beyond their shrunken horizons. The observable universe is a window that's slowly closing. Every day, more light slips past the horizon for the last time. Every day, we lose visibility of galaxies we'll never see again. The universe is saying goodbye, one photon at a time, to everything beyond our reach. But for now, the window is open. The view is spectacular. 2 trillion galaxies, more stars than grains of sand on Earth, distances that numbers can name but minds cannot grasp, and you're seeing it. You're alive during the era when seeing is still possible. That's something. Let's imagine you could travel at the speed of light. Forget the physics that makes this impossible. Forget that anything with mass would require infinite energy to reach light speed. Forget relativistic effects. Forget everything practical. Just imagine you wake up tomorrow with the ability to move at 299,792 kilometers per second. You'd be the fastest human who ever lived, capable of circumnavigating Earth over 7 times before your morning coffee finished cooling. How long would it take you to reach the nearest star? At light speed, Proxima Centauri is 4.24 years away, not reduced to minutes, not made trivially quick. Over 4 years, you'd leave Earth as one person and arrive at Proxima as someone 4 years older, having spent every moment of that time in transit. You'd miss birthdays, holidays, world events. You'd age. The journey, even at literally the fastest possible speed, would consume significant chunks of your finite human lifespan. And Proxima is the nearest star. It's the tutorial level, remember? The center of our galaxy is about 26,000 light-years away. Even at light speed, you couldn't reach it within a human lifetime. You'd need 26,000 years, about 1,300 generations. The nearest large galaxy, Andromeda, is 2.5 million light-years distant. To reach it at light speed, you'd need 2.5 million years. Human civilization is only about 10,000 years old. You'd be travelling for 250 times the entire duration of recorded history. This is why interstellar travel is science fiction. Not because we lack the engines or the fuel or the will, but because the distances are fundamentally incompatible with human biology. We evolved for a small planet with a narrow horizon. We live for maybe a century if we're lucky. The universe is structured on timescales that make century-long lifespans irrelevant. Even the speed of a light, the universal maximum, the absolute fastest, is too slow for cosmic distances to be practically traversable. Scholars still argue about whether faster-than-light travel might be possible through exotic means. Warp drives, wormholes, manipulation of space-time itself. These concepts appear in physics equations without being definitively forbidden. The Alcubierre drive, proposed in 1994, describes a theoretical bubble of warped space-time that could move faster than light, while the contents of the bubble remain stationary relative to local space. The catch is that it requires exotic matter with negative energy density, which may not exist, and the amounts required would be more than the mass of Jupiter. Wormholes, shortcuts through space-time, are allowed by general relativity, but would likely collapse instantly without exotic matter to hold them open. Every proposed method of faster-than-light travel requires something we don't have and may never have. Here's a quirky consolation. If you did travel at close to light speed, time would slow down for you relative to the outside universe. This is time dilation, one of Einstein's weirder gifts. A spacecraft moving at 99% of light speed would experience time about 7 times slower than stationary observers. 99.9%, about 22 times slower. At very close to light speed, you could theoretically reach distant stars within a human lifetime, from your perspective. The catch is that everyone you left behind would age normally. Travel to a star 50 light-years away at 99% of light speed, and you'd experience about 7 years. But when you returned, 100 years would have passed on Earth. Everyone you knew would be dead. You'd be a stranger from the past visiting a future that forgot you. This isn't theoretical. Time dilation has been measured with atomic clocks on airplanes and satellites. It's real. It happens. The faster you move, the slower your time passes relative to those at rest. At the speeds required for interstellar travel, the effects would be dramatic. Useful for the traveller, devastating for their relationships. The universe seems designed to keep things apart. Not maliciously, not intentionally, but structurally. The speed limit isn't a rule someone imposed. It's built into the fabric of space-time itself. Distances between stars are vast because the universe is vast and things are spread thin. The impossibility of practical interstellar travel isn't a failure of human engineering. It's a consequence of how reality works. We're trapped not by our technology, but by the mathematics of existence. And yet, something in humans refuses to accept this. We send probes, we beam radio signals, we write science fiction about what it would be like to visit other stars, other galaxies, other worlds. We're a species that evolved to explore, and finding an unexplorable universe is spiritually uncomfortable. Maybe future generations will solve problems we can't yet formulate. Maybe the physics we know is incomplete. Maybe there are loopholes nobody has discovered. Or maybe the universe really is too large for us, and we'll spend eternity staring at stars we can never touch. For tonight, though, none of that matters. You're not travelling anywhere. You're lying still, breathing slowly, letting the weight of cosmic distances settle around you like a blanket. The stars are impossibly far, and that's okay. They're still beautiful from here, still present in their ancient delayed way, still telling their stories to anyone patient enough to receive them. You don't need to reach the stars to appreciate them. You just need to look up, let their light find you, and accept that some things are meant to be admired from a distance. You're still here, still resting perhaps, but your mind hasn't quite let go of the cosmic strangeness we've been exploring. That's fine. The universe isn't going anywhere, and neither are you, not for a while yet. Let's talk about something that makes the already impossible distances even stranger. Time itself behaves differently depending on how fast you're moving. You've heard of time dilation, probably. It shows up in science fiction whenever a writer wants to create poignant separation between characters. The astronaut who returns younger than their twin, the space explorer who arrives home to find centuries have passed. These stories feel like fantasy, like dramatic license taken with physics for emotional effect. They're not. Time dilation is real, measured, confirmed by experiments ranging from particle accelerators to GPS satellites. It's one of the universe's more unsettling features, and it gets weirder the deeper you look. Einstein figured this out in 1905, the same year he explained the photoelectric effect and laid groundwork for quantum mechanics. It was an extraordinary year, the kind that makes you wonder what was in the water in Switzerland. His special theory of relativity contained a revolutionary proposition. Time passes at different rates depending on your velocity relative to other observers. There's no universal clock ticking identically for everyone. Time is local, personal, elastic. Here's how it works. Imagine you have a twin. You stay on Earth. Your twin boards a spacecraft that accelerates to 90% of light speed and travels to a star 10 light years away, then turns around and comes back. From Earth's perspective, the journey takes about 22 years, 11 years each way at 90% of light speed, plus a bit more for acceleration and deceleration. When your twin steps off the ship, you're 22 years older than when they left. But your twin is only about 10 years older. They've aged less than half as much. Their clocks, their heartbeats, their biological processes, everything ran slower from Earth's perspective while they were moving at high velocity. From their perspective, everything felt normal. They didn't experience slow motion or unusual sensations. But the math is inescapable. High speed means slow time. Relative to stationary observers, moving clocks tick slowly. This isn't science fiction. In 1971, physicists flew atomic clocks on commercial airplanes around the world and compared them to identical clocks that stayed on the ground. The flying clocks lost time, not much, just nanoseconds, but exactly the amount predicted by relativity. GPS satellites, which orbit Earth at high speeds, have their clocks adjusted to compensate for relativistic effects. Without this adjustment, GPS would drift by about 10 kilometers per day. Every time you use navigation on your phone, you're benefiting from Einstein's equations. Scholars still argue about the philosophical implications of time dilation. What does it mean for two observers to experience different rates of time? Is there a real time that exists independently of observers? General relativity, which extends special relativity to include gravity, makes things even more complicated. Time also slows down in strong gravitational fields, meaning someone on a mountaintop ages slightly faster than someone at sea level. The universe doesn't seem to have a master clock. Time is relative, local, personal. Here's a quirky thought experiment that physicists love to debate: the twin paradox. If motion is relative, why can't the travelling twin claim they were stationary while Earth moved away and back? Wouldn't both twins then expect the other to be younger? The resolution involves acceleration. The travelling twin is the one who changes direction, who experiences non-inertial motion, and this breaks the symmetry. The twin who accelerates is definitively the one who experiences less time, but the details get contentious, and textbooks have argued about the best explanation for over a century. Time dilation has profound implications for interstellar travel. If you could build a ship capable of accelerating continuously at one Earth gravity, a comfortable Earth-like pull that would let you walk around normally, you could reach astonishing destinations within a human lifetime. 1 year of acceleration at 1g gets you to about 77% of light speed. 2 years of acceleration, then 2 years of deceleration could get you to Alpha Centauri in about 6 years of ship time, though 40 years would pass on Earth. With enough fuel, you could reach the galactic center in about 20 years of ship time, but 30,000 years would pass on Earth. You could theoretically travel to distant galaxies and back within a human lifetime, but millions or billions of years would pass in the universe you left behind. This creates a strange kind of loneliness. Even if faster-than-light travel remains impossible, relativistic travel could let individuals cross vast distances, but they'd be one-way trips into the future. You could visit a star system and return, but everyone you knew would be long dead. Civilizations would rise and fall while you aged a few decades. You'd be a time traveler, not into the past, but into the future, with no way back. The universe at high speeds becomes a place of profound temporal isolation. Light years aren't just distances, they're potential lifespans, years of separation, generations of change. Even if we could build ships that travelled at near light speed, the human cost of using them would be enormous. The distances between stars aren't just spatial barriers, they're temporal ones too. And here's the strangest part. From the perspective of light itself, time doesn't pass at all. A photon travelling from a distant star experiences no time between its emission and its absorption. The billion-year journey from the photon's frame of reference is instantaneous. Light exists outside time in a way that matter never can. The very thing we use to measure cosmic distances is itself exempt from the duration it imposes on everything else. You're lying in a universe where time isn't fixed, where speed stretches and compresses duration, where light crosses billions of years without experiencing a single moment. Your time is passing normally because you're effectively stationary. But somewhere out there, particles in accelerators are aging slowly, astronauts on space stations are aging slightly slower than their families on Earth, and light is travelling through the void in an eternal present that never experiences the years it creates for everyone waiting on the other end. Time is stranger than distance. Distance just tells you how far apart things are. Time tells you how long you'll be apart, and it cheats. Before there were stars, before there were galaxies, before there were atoms in any configuration you'd recognise, there was light. The oldest light in the universe. Light that has been travelling for nearly 13.8 billion years, carrying information about the moment the cosmos first became transparent. This is the cosmic microwave background, and it is everywhere, filling all of space, whispering the story of creation to anyone with the tools to listen. You can't see it with your eyes. The cosmic microwave background peaked in visible light once, shortly after the universe's birth, but the expansion of space has stretched those photons into microwaves, wavelengths far too long for human vision. The light is still there, it fills every cubic centimetre of space, but it's been redshifted into invisibility. To detect it, you need radio telescopes and microwave receivers, instruments that can sense the gentle hum of radiation that permeates everything. The cosmic microwave background was discovered by accident in 1965. Two engineers at Bell Telephone Laboratories, Arno Penzias and Robert Wilson, were trying to calibrate a sensitive radio antenna and couldn't get rid of a persistent static. They checked everything. Pigeons nesting in the antenna, equipment malfunctions, interference from nearby cities, but the noise remained. It was coming from every direction, constantly, uniformly. Eventually they realised they were detecting something cosmological, the afterglow of the Big Bang, predicted by theorists but never before observed. They won the Nobel Prize for stumbling onto the most ancient light in existence. Here's what that light tells us. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms. Before this, space was filled with a fog of charged particles that scattered light constantly, making the universe opaque. After recombination, light could finally travel freely. The photons released at that moment have been travelling ever since, crossing billions of light years, witnessing the formation of the first stars and galaxies, carrying information about the universe's infancy. When we look at the cosmic microwave background, we're seeing the universe as it was 380,000 years old. Not the actual Big Bang, but close. The surface we're observing is called the surface of last scattering, the moment when light finally broke free of the primordial fog. It's like looking at the wall of a cloud. You can't see what's inside, but you can see the surface where visibility begins. The cosmic microwave background isn't perfectly uniform. It has tiny variations, spots slightly warmer or cooler than average by about 1 part in 100,000. These variations are cosmically important. They represent density fluctuations in the early universe, regions where matter was slightly more or less concentrated. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter, became denser still, and eventually collapsed to form galaxies and galaxy clusters. The variations in the cosmic microwave background are the seeds of everything. Every star, every planet, every living creature owes its existence to those ancient density ripples. Scholars still argue about what caused the initial fluctuations. The leading theory is cosmic inflation, a period of exponential expansion in the universe's first fraction of a second, which would have stretched quantum fluctuations to cosmic scales. But inflation is controversial. Some physicists accept it as proven, others consider it speculative. The cosmic microwave background is consistent with inflationary predictions, which is encouraging, but alternative explanations exist. The beginning of everything remains scientifically unsettled. Here's a quirky detail about the cosmic microwave background. It has a temperature, specifically about 2.7 Kelvin, or roughly minus 270 degrees Celsius. This is the temperature of the universe itself, the baseline temperature that space would cool to if all other heat sources were removed. The cosmic microwave background fills space with a faint warmth that isn't quite cold enough to be absolute zero. Even the emptiest voids with nothing visible for billions of light years are gently warmed by this ancient radiation. The cosmic microwave background is the farthest thing we can ever see. Beyond it lies the opaque fog of the early universe, and beyond that, the Big Bang itself. Events we cannot observe because light couldn't escape to tell us about them. The cosmic microwave background is a wall, beautiful and informative but fundamentally opaque to everything that came before. And here's what's truly remarkable: you're bathing in it right now. The cosmic microwave background passes through walls, through your body, through everything. About 400 photons from the cosmic microwave background occupy every cubic centimetre of space, including the space you're in. They're all around you, ancient light from the dawn of creation, passing through you constantly, unnoticed, unfelt. You're surrounded by the universe's oldest light, and you'll never see it, never sense it, never know it's there except by reading about it in moments like this. The light that tells us how the universe began is also the light that defines the limits of what we can know. We can see back 13.8 billion years, but no farther. We can watch galaxies evolve across cosmic time, but we'll never see the Big Bang itself. The cosmic microwave background is both a window and a barrier, offering extraordinary information about the past while blocking anything more ancient. Somewhere in that ancient light, in those tiny temperature variations, is the seed of the atom that eventually became you. The matter that makes up your body was forged in stars, yes, but before that, it was dense plasma in the early universe, contributing to the fluctuations that the cosmic microwave background records. You are, in a very literal sense, looking at your own ancestors when you study that radiation. The universe's first chapter contains a page with your name on it, written in temperature variations too small to feel but large enough to create everything. The oldest light in existence has been travelling toward you since before Earth, before the Sun, before the Milky Way took its current shape. It arrives tonight, as it has arrived every night, filling space with its quiet hum, its ancient warmth, its record of the moment everything began. Telescopes are time machines. This isn't a metaphor or a poetic flourish, it's literal. When astronomers point their instruments at distant objects, they're not seeing those objects as they currently exist. They're seeing them as they were when the light left, which for distant galaxies means millions or billions of years ago. Every observation is archaeology, every image is a fossil. Consider the Hubble Space Telescope, which has been orbiting Earth since 1990. When Hubble photographs a galaxy a billion light-years away, the image shows that galaxy as it was a billion years ago. Complex life on Earth was just beginning to emerge. The first multicellular organisms were experimenting with bodies and senses. Everything that would become fish, dinosaurs, mammals, humans, all of it lay in the future. The light leaving that distant galaxy at that moment has been travelling ever since, and it's finally arriving now, captured by a telescope named after the astronomer who proved galaxies existed at all. The farther we look, the deeper we see into the past. The James Webb Space Telescope, launched in 2021, can detect galaxies that formed just a few 100 million years after the Big Bang. These are among the earliest galaxies ever observed, infant structures in a young universe, their light travelling for over 13 billion years to reach us. We're seeing them as they were when the universe was less than 5% of its current age. Babies, cosmically speaking, though each one contains billions of stars. This has practical consequences for understanding cosmic evolution. We can't watch a single galaxy age. That would take billions of years. But we can observe millions of galaxies at different distances, which means different ages, and piece together a timeline. We see young galaxies far away and old galaxies nearby, and from this mosaic we reconstruct how galaxies form, grow, merge, and die. It's like studying human development by photographing people of different ages rather than following one person through their lifetime. Scholars still argue about certain aspects of this cosmic archaeology. The earliest galaxies observed by the James Webb Space Telescope seem surprisingly large and well-formed for their age, larger than models predicted. Some astronomers think this means we need to revise our understanding of early galaxy formation. Others think we're misinterpreting the data, that these galaxies are smaller than they appear, or that our distance estimates are off. The debate is ongoing, which is how science works. New observations challenge old models, and either the observations get explained or the models get replaced. Here's a quirky implication of telescopes being time machines. We can never see the present state of anything outside our immediate vicinity. The Sun is 8 minutes old when we see it. Proxima Centauri is over 4 years old. Andromeda is 2.5 million years old. The cosmic microwave background is 13.8 billion years old. There's no now that we can observe across cosmic distances. The universe we see is a composite of moments, layered by distance, with the present forever hidden behind light speed delays. This means that somewhere out there, intelligent beings might be observing us, but they'd be seeing Earth's past. A civilization 40 light-years away, if it had good enough telescopes, could watch the 1980s right now. A civilization 1,000 light-years away could watch medieval Europe. A civilization 65 million light-years away could watch the asteroid strike that killed the dinosaurs. The past is still out there, propagating through space, available to anyone with the technology to catch it. And the same is true in reverse. Light from Earth is spreading outward at light speed, carrying information about our planet's history to anyone who might intercept it. The first television broadcasts from the 1930s have now travelled almost 100 light-years, potentially reaching thousands of star systems. Whether anyone is listening is another question, but the broadcasts are out there, expanding in a shell around Earth, evidence of our civilization travelling through the cosmos. every embarrassing moment ever recorded is technically preserved in light, somewhere, propagating forever. Telescopes also let us witness cosmic events that already happened. Supernovae observed today exploded hundreds or thousands of years ago. We're just now getting the news. The supernova that created the Crab Nebula exploded in 1054, observed by Chinese astronomers, but the explosion itself happened about 6,500 years earlier. The astronomers in 1054 were seeing an event from roughly 5,450 BCE, about the time humans were inventing writing. The light carried news of a stellar death that happened while civilization was still learning to record information. The time machine quality of telescopes creates strange possibilities. If you could somehow travel faster than light to a point 100 light years away, then stop and observe Earth, you'd see Earth as it was 100 years ago. Travel 1,000 light years away, see 1,000 years ago. In principle, with enough speed and distance, you could observe any moment in Earth's history, though you'd need impractical amounts of energy and technology that may never exist. The information is out there, spreading at light speed, theoretically accessible to anyone who could get ahead of it. For now, we're limited to the observations we can make from here, using light that has travelled to us rather than light we've travelled to intercept. But even with that limitation, we've reconstructed the history of the universe from its first moments to the present. We know what galaxies looked like when they were young. We know what stars looked like when the universe was dense and hot. We know the temperature of space 380,000 years after the Big Bang. All of this knowledge comes from light that has been travelling toward us for eons, patiently crossing the void, carrying information about moments long since past. The universe is a library, and every telescope is a reader, accessing chapters written billions of years ago, still available because light never stops travelling, and space is large enough to preserve everything. When you look at the stars tonight, or when you imagine looking as your eyes grow heavy, you're reading that library too, faint and incomplete, but real. Here's where the universe stops making intuitive sense. You've accepted that light has a speed limit. You've accepted that distances are vast. You've even accepted that looking far away means looking back in time. But now we need to talk about the expansion of space itself, and this is where reality gets truly strange. Space is stretching, not objects flying apart through space, but the actual fabric of space-time expanding, carrying everything with it. This was discovered in 1929 by Edwin Hubble, who noticed that distant galaxies are moving away from us, and that the farther they are, the faster they recede. The relationship is linear. A galaxy twice as far moves away twice as fast. This became known as Hubble's law, and it implied something revolutionary. The universe isn't static, it's growing. The expansion isn't happening from a centre. There's no point in space that's the middle of the explosion, no location you could travel to that represents where the Big Bang happened. The Big Bang happened everywhere. Every point in space was once close to every other point, compressed into a dense, hot state that expanded into everything we see. The expansion is happening uniformly, like dots on a balloon that spread apart as the balloon inflates. No dot is the centre. Every dot sees every other dot receding. This creates a bizarre situation for distant galaxies. The most distant objects we can observe are receding from us faster than the speed of light. Not because they're moving through space at superluminal velocities, that's still impossible, but because the space between us is expanding so rapidly that the total recession rate exceeds light speed. If you add up all the stretching happening between here and there, the cumulative effect can be faster than light. This doesn't violate relativity. Nothing is moving through local space faster than light. The speed limit applies to motion through space-time, not to the expansion of space-time itself. The universe found a loophole. It can't throw objects faster than light, but it can grow faster than light would take to cross. The The distinction is subtle but physically meaningful. The expansion is accelerating. This was discovered in 1998, and it won the Nobel Prize in 2011 because it was so unexpected. We thought gravity would be slowing the expansion, pulling everything back together. Instead, distant supernovae revealed that the expansion is speeding up. Something is pushing the universe apart, counteracting gravity, driving space to stretch faster and faster. We call this something dark energy, and we have no idea what it is. Dark energy makes up about 68% of the universe's total energy content. Dark matter makes up about 27%. Ordinary matter, stars, planets, gas, everything you've ever seen or touched, makes up less than 5%. The universe is almost entirely dark. Dark energy pushing space apart and dark matter holding galaxies together, neither of which we can directly observe or explain. Scholars still argue about the nature of dark energy. It might be the cosmological constant, a fixed energy density inherent to empty space. It might be a dynamic field that changes over time. It might be a sign that our theory of gravity is wrong on cosmic scales. We don't know. The observations are clear, but the explanation remains elusive. Here's a quirky detail. Empty space has energy. The cosmological constant interpretation of dark energy suggests that vacuum, true empty vacuum, with nothing in it, has a positive energy density. This energy doesn't clump like matter. It's spread uniformly throughout space. As space expands, there's more space, which means more vacuum energy, which drives more expansion. It's a cosmic feedback loop that ensures the expansion will continue forever. The accelerating expansion has grim implications for the far future. As space stretches faster and faster, distant galaxies will recede beyond the observable horizon. Eventually, the only galaxies visible will be those gravitationally bound to our local group. The night sky will empty. Cosmological evidence of the Big Bang will fade. Future civilizations might look up at a lonely universe and have no way to know that trillions of galaxies once shone beyond their sight. Even more dramatically, if the acceleration increases enough, space might eventually stretch faster than gravity can bind galaxies, then stars, then planets, then atoms. This scenario is called the Big Rip, and it's one possible fate of the universe. Everything torn apart by expansion, down to the subatomic level, in a final dissolution of all structure. Most physicists consider this unlikely. The evidence suggests dark energy's strength is constant rather than increasing. But the possibility remains open. You live in a universe that is growing. Every second, space is a little bigger than it was before. The distances you've been contemplating aren't fixed. They're increasing. The light years between galaxies are being added to constantly, stretched by expansion, making the already impossible distances even more impossible. And yet here, locally, expansion doesn't matter. The room you're in isn't stretching. Your body isn't expanding. Gravity and electromagnetic forces hold everything together on small scales. Expansion only dominates where the distances are vast and the binding force is weak. In your corner of the universe, things are stable. The chaos is happening far away, silently, invisibly, affecting objects you'll never see and places you'll never reach. The universe is expanding, it's accelerating, something dark is driving it. And none of that changes the fact that you're here, in this moment, on this planet, resting while the cosmos silently grows around you. The expansion doesn't need your attention. It'll continue whether you're awake or asleep, aware or oblivious, at peace or full of wonder. The universe is getting bigger. Let that be someone else's problem for tonight. Some places in the universe are forever beyond our reach, not because our technology isn't advanced enough, not because we haven't tried hard enough, but but because the structure of space-time itself makes them inaccessible. These are the regions beyond the cosmic horizon, the places we can never visit, never observe, never even know exist in any direct way. Remember how distant galaxies are receding faster than light due to the expansion of space. That creates a boundary. There's a distance at which galaxies are receding exactly at light speed. Beyond that distance, they're receding faster than light. Light from those galaxies, even if it started travelling toward us, would never arrive. Space is expanding faster than the light can cross it. We call this the cosmological event horizon, and it's different from the observable universe's edge. The observable universe is defined by how far light has travelled since the Big Bang. It's a sphere about 93 billion light-years across, centred on Earth, or any observer. We can see everything within it because light from those regions has had time to reach us. But within the observable universe, some objects are already beyond the event horizon. We can see them. They're left long ago when they were closer. But if we tried to send a message or a spacecraft, we'd never reach them. The space between us is growing too fast. This is cosmologically depressing if you dwell on it. The universe is full of galaxies we can see but never touch. They're there, right in front of us in our telescopes, but they're already ghosts of accessibility. As the expansion accelerates, more galaxies will slip beyond the event horizon. The reachable universe is shrinking, even as we observe distant wonders that drift forever out of range. Scholars still argue about exactly where the event horizon lies and how it will evolve over time. The calculations depend on the behaviour of dark energy, which we don't fully understand. If dark energy's density remains constant, the horizon stabilizes at a certain distance. If dark energy's density changes, the horizon could grow or shrink. The uncertainty in our understanding of dark energy translates directly into uncertainty about the limits of our cosmic reach. Here's a quirky thought experiment. Imagine an advanced civilization at the edge of our observable universe, 45 billion light-years away. They see us in their past, just as we see them in their past. But neither civilization can ever visit the other. The space between us is expanding faster than any ship could cross. We're cosmologically separated, visible but unreachable, neighbours who will never meet. The universe allows us to see them but forbids us to touch. This might be the answer to the Fermi paradox, at least partially. If the universe is large enough and expansion is fast enough, civilizations might be isolated islands, each visible to others but none able to communicate on timescales shorter than cosmic. Messages sent at light speed might never arrive. Ships sent at near light speed might never reach their destinations. The universe could be full of intelligent life, each species trapped in its own bubble of reachable space, waving at neighbours who'll never wave back. The cosmic horizon also means we'll never know the universe's true size. Whatever lies beyond the observable universe is, by definition, unobservable. There could be more galaxies, different physics, infinite variations on the cosmos we know, and we'd never detect any of it. The universe could be 100 times bigger than what we see, or infinitely larger, or finite but curved, and we have no way to directly check. The horizon is not just a limit on travel, it's a limit on knowledge. Some physicists speculate about what lies beyond. Inflation suggests that our observable universe is a tiny patch of a much larger cosmos, with regions so far away they might have different physical constants. The multiverse hypothesis suggests our universe might be one of many, each with its own space-time, unreachable from any other. These ideas are speculative, perhaps untestable, existing at the boundary between physics and philosophy. For practical purposes, humanity is confined. Even with hypothetical advanced technology, the reachable universe has limits. If we colonized the galaxy, built fleets of interstellar ships, spread across millions of star systems, the expansion of space would still cage us. Eventually, even the most ambitious journey would find itself in a race against expansion, with expansion winning. The universe isn't just large, it's actively growing, actively escaping, ensuring that most of creation remains forever out of reach. Tonight, some of that unreachable creation is visible in your sky. If you walked outside, away from city lights, and looked at the faint smudges between familiar stars, some of those smudges are galaxies already beyond your horizon. You're seeing their past, their ancient light, but they've already crossed the threshold into inaccessibility. The universe showed them to you, then took them away, keeping only the memory. This could be melancholy, and for some people it is. The vastness of the unreachable can feel like loss. But there's another way to see it. The universe is so large, so rich, so full of structure and history and possibility, that even being confined to a small fraction of it leaves more than we could ever explore. The local group alone contains enough stars and planets to keep humanity busy for billions of years. The reachable universe, even shrinking, contains wonders beyond counting. You don't need to reach everywhere to have enough. You don't need to see everything to have seen marvels. The horizon exists, limiting and final, but within it, within the bubble of light that has reached you, within the space that remains accessible, there's more than any species could exhaust. The unreachable places will continue without us. The reachable places are more than enough. After all of this, the light years, the galaxy clusters, the expanding universe, the cosmic horizons, you might be wondering why any of it matters. You're a single human on a single planet, living for a cosmological eye blink, unable to visit even the nearest star. The universe is vast beyond comprehension, and you are small beyond notice. What's the point of knowing how large and empty it all is? This is a fair question. It deserves a fair answer. The first thing to say is that knowing doesn't have to be useful to be valuable. Humans have always looked at the sky and wondered. Long before astronomy could navigate ships or predict eclipses, people told stories about the stars, gave them names, made them meaningful. The urge to understand the cosmos seems built into us, as fundamental as the urge to understand ourselves. Knowing the universe is vast and ancient and strange satisfies something deep, something that doesn't demand practical application. But there are practical implications too. Understanding cosmic distances helped us recognize that we are not the center of the universe. A humbling lesson that echoes through philosophy, religion, and culture. Copernicus moved Earth from the center. Hubble moved the Milky Way from the center. The cosmic microwave background showed us we're one of countless possible observers, each with their own horizon, none privileged. This humility changes how we think about ourselves, our place, our importance. Scholars still argue about whether cosmic humility is psychologically healthy. Some people find the universe's vastness crushing, a source of existential dread. Others find it liberating, a release from the pressure of cosmic significance. If you're a tiny blip in an incomprehensibly large universe, then maybe your failures don't matter much. Maybe your mistakes won't echo through eternity. Maybe you're free to be small, to be temporary, to enjoy what you have without the weight of cosmic consequence. Here's a quirky comfort. The universe is old and large and indifferent, but it also produced you. The atoms in your body were forged in stars that exploded billions of years ago. The elements that make up your bones, your blood, your brain, carbon, oxygen, iron, calcium, all of it was cooked in stellar cores and scattered across space by supernovae. You are quite literally made of star stuff. The universe isn't separate from you, you're part of it. A local condensation of cosmic material that briefly became aware of itself. This perspective doesn't solve anyone's problems, Knowing you're made of star stuff won't pay your bills or heal your heartaches, but it provides context. The vastness that seems to diminish you is also your ancestry, your origin, your material history. You belong to the cosmos in the most literal possible way. The light years that separate stars also connect them, part of the same expanding fabric that eventually, through billions of years of physics and chemistry and biology, produce something capable of wondering about it all. The universe is hostile to life. Space is mostly vacuum, too cold or too hot, bombarded by radiation, lacking the gentle conditions that biology requires. And yet, here you are. Against all odds, on a small rocky planet in the habitable zone of an ordinary star, in a quiet corner of an average galaxy, life arose and evolved and eventually developed the capacity to contemplate its own context. The hostility of the cosmos makes the existence of life more remarkable, not less. You're not diminished by the vastness, you're miraculous within it. There's also something to be said for perspective. When the universe is 93 billion light-years across and 13.8 billion years old, human concerns take on a different character. The argument you had last week, cosmically invisible. The deadline stressing you out, cosmically irrelevant. This isn't to say those things don't matter to you. They do, because you're human, and human concerns are real and valid. But it can help to remember the scale. The universe has been expanding for billions of years without caring about your schedule. It'll continue expanding after you're gone. You're not obligated to solve cosmic problems because you're not a cosmic being. You're a local one, and local concerns are enough. Tonight, you've travelled far. You've crossed light years and galaxy clusters and the expanding void. You've touched the edge of the observable universe and mourned the unreachable places beyond, and through it all, you've remained exactly where you started, here in your small warm corner, breathing, resting, alive. That's not nothing. In a universe this large, in a cosmos this ancient, being alive and aware is extraordinary. The chance that any particular arrangement of atoms would become conscious is infinitesimally small, and yet here you are, defying the odds, existing against the probability. The universe made you without meaning to. You're an accident of physics, a byproduct of stellar evolution, a local anomaly in a vast cold emptiness. And accidents can be beautiful, byproducts can be precious, anomalies can be worth protecting. The universe doesn't care about you, but you can care about the universe, and about yourself, and about the other small warm anomalies sharing this unlikely planet. That caring is its own kind of significance, local and temporary and real. You matter because you're here. The universe is vast and you're small, and that's okay. The stars are still there. They've been there since before you opened your eyes, before you learned their names, before anyone lived who could name them at all. They'll be there long after you close your eyes tonight, after you've forgotten everything you learned, after the brief flicker of your consciousness has dissolved back into the cosmic background from which it came. The stars don't care whether you're watching. They shine anyway. But tonight, you are watching, or you were earlier before your eyes grew heavy. And for a little while, you held the universe in your mind. Light years stretched across your thoughts, galaxies spun in your imagination. The cosmic microwave background hummed at the edge of your awareness, ancient light from the dawn of everything, filling space, filling the room, filling you without your ever noticing. You've travelled far tonight, farther than your body will ever go. You've crossed the 4.24 light years to Proxima Centauri, our nearest stellar neighbour, close by cosmic standards but impossibly distant by any other. You've spanned the 100,000 light years of the Milky Way, our home galaxy, our cosmic address, the island of stars that contains every sun you've ever seen. You've drifted 2.5 million light years to Andromeda, our approaching neighbour. the smudge in the sky that carries 1 trillion stars toward an embrace 4 billion years from now. You've touched the edge of the observable universe, 46 billion light-years away, where light from the beginning of everything is still arriving, still telling stories about a young cosmos that barely resembled the one we know. You've mourned the places beyond the horizon, the galaxies receding faster than light, the regions we can see but never reach, the unreachable forever. And you've come back, here, to this room, to this moment, to your body, breathing slowly, settling into rest. The universe is vast. This is the truth you've carried tonight, the weight you've borne while lying still. It's vast and old and largely empty, filled with distances that mock human scale, structured on timescales that make lifetimes irrelevant. The light year is our attempt to measure it, our desperate tape measure stretched across the void, and even with that tool the numbers spiral into incomprehension. But here's what else is true. You comprehended some of it. Not all, nobody comprehends all, but some. Enough. You held in your mind, however briefly, the distance to the nearest star and the depth of the cosmic web and the age of the oldest light. You understood, as well as any mind can understand, that you exist in a universe so large that your existence within it is statistically absurd. And you kept breathing, you kept resting, you didn't panic. That's something. That's actually remarkable. A few hundred years ago, humans didn't know other galaxies existed. A few thousand years ago, stars were mysterious lights hung in a crystal sphere. The knowledge you've absorbed tonight, casually, while trying to fall asleep, represents the accumulated wonder of countless scientists across centuries, each one pushing the boundaries of what could be known. You've inherited their work, you've received their gifts, and now you can let it go. The numbers don't need to stay in your head. The distances don't need to haunt you. The universe will continue expanding whether you remember its dimensions or not. The stars will keep shining. The light will keep travelling. The cosmic microwave background will keep whispering its ancient story to anyone with the tools to listen. Your job right now is much simpler. Your job is to rest, to let your muscles soften, to let your thoughts slow, to surrender gently to the sleep that's been waiting at the edges of your awareness since we began. The universe is vast and you're small, and tomorrow you'll wake up and face the local concerns of a local life on a local planet. The light years will still be there, unchanged, waiting for the next time you look up. The galaxies will continue their slow dance. The expansion will accelerate. The cosmic horizon will recede. None of that needs you tonight. Tonight, you can simply be. A small, warm anomaly. A brief arrangement of atoms that somehow learned to wonder. A consciousness that stretched across light years without ever leaving the room. You did well. You travelled far. Now come back. Come all the way back. To here, to now, to the soft surface beneath you, and the quiet sounds around you, and the gentle rhythm of your own breathing. The stars are still there. They'll wait. They've been waiting for billions of years. They can wait a few more hours. Close your eyes. Let the universe take care of itself. Sleep now. And so the light continues its ancient journey. From stars you'll never visit, across voids you'll never cross, carrying stories written in wavelengths your eyes translate into wonder. The photons don't know you're sleeping. They don't know anything. They simply are travelling, always travelling, at the only speed they've ever known. Somewhere right now, light is leaving a star that won't reach Earth for 1,000 years. Somewhere else, light that left before the dinosaurs died is finally arriving, completing a journey that spans more time than your species has existed. The universe is a tapestry woven from travelling light, threads stretching across billions of years, connecting moments that have no business being connected, making the past visible to the present in ways that physics allows but intuition struggles to accept. You are part of this tapestry. Your existence is one of its threads, brief and local but real. The atoms in your body will outlast you, recycling through stars and planets, and perhaps, someday, other beings who will look up at their own skies and wonder their own wonders. For now, though, you rest. The light travels, the universe expands, and in this small warm corner, nothing needs to happen except the slow, easy slide into sleep. The distances that seemed so vast are far away now, receding like dreams at the edge of waking, leaving only peace, only stillness, only the quiet certainty that you are here, you are safe, and the stars will keep their vigil while you rest. Let go. Drift. The universe will hold you while you sleep.